As part of our activity this week is to do exponential smoothing as well as moving averages. I wanted to do a quick PowerPoint on the difference between the two and actually how to use forecasting effectively. Managers really try to deal with uncertainty by using all kinds of different forecasting tools. Of course, heuristics, rules of thumb, intuition, seat of the pants are many of the approaches people use, but even more importantly, moving averages, exponential smoothing, trend projections, least squares regressions are also used. We're going to be spending our time with moving averages, exponential smoothing, and linear regression. 8 steps. I'll go through this real quickly, but first, determine the use of the forecast. What are you trying to obtain? Number two, select the items or quantities you're going to be forecasting. Determine the time horizon. Is it 10 months, 12 months, 10 years? What is it specifically? Select the forecasting model or models. Gather the data needed to make the forecast. Validate that forecast by actually beginning to run the tool, whether it's moving averages or exponential smoothing, and then make the forecast and implement the results. There are a number of different tools, qualitative tools like Delphi, jury of executive opinion, others. Time series methods are also important ones, exponential smoothing, trend projections, and then there are causal methods like regression analysis that we'll be using later. Time series is our focus. Moving averages, exponential smoothing, trend projections are going to be our focus. And of course, we set these up on a Cartesian plane. We're looking at, actually, this looks like a linear model. Let me bring down so you can see the x-axis, but we're looking at time in years and annual sales in order to determine what is the most effective approach. Anytime you can present this data in a more intuitive fashion, the better off your decision makers will be. When we look at the actual values and our forecasts, we're given the opportunity to identify our forecast error and subtracting the actual value that comes up versus what we forecast, we're able to get our forecast error, and we can calculate a statistic called the mean absolute deviation. The mean absolute deviation is the standard normally for working with forecasting models like exponential smoothing, regression, linear regression, and moving averages. And it's a really simple statement. Basically, you take the amount of forecast error. We can see, for instance, the actual numbers of CDs sold at 110 minus our forecast of right here of 110, 100 minus 110 is equal to 10. 120 minus our forecast of 100. What is that? 120 minus 1 hum. Gonna have to look at that. That's an error. But you get it. You would add all those errors up. You would get your sum of errors, 160. You would divide that by the number of years that we're using in this situation. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we would get a mean absolute deviation of 17.8. It's not rocket science. I'll bring that down a little bit. But it does give us an opportunity to compare one forecast against another. We have a situation here. We'll be playing with this data set generally, but hospital days, forecasting error, and you can see all the forecasts, and you can also see the actual data that came up. And again, that allows us to understand the amount of error in our model so we can deal with that. But the time series is a sequence of really evenly spaced events, whether it's weekly, monthly, or quarterly. We don't care about other data, whether it's incredibly valuable or not. We're interested in predicting the future based on that sequence of evenly spaced data. To look at that data or actually to look at moving average of one of our two models, all we're really doing here, if we're doing a 3-period moving average, is taking 3 of our data, actual, and let's say actual, for a 3-period moving average divided by the number 3, and that gives us our forecast. I'll show you this more explicitly in a couple of minutes, but our Y is our actual data, and our F is our forecast, and of course the N are the number of periods that we're going to be averaging. So when we look at Wallace Garden Supply, they're collecting data over a period of time. Again, we're looking at a 3-month moving average. And we can see here that we've got 12 months of data that we're working with. We take the first 3 of actual sales, 10, 12, 13. 10, 12, 13. We divide by 3, and that gives us our forecast of 11.67. We then, for the next one, take our 12, 13, 16. 12, 13, 16 divided by 3 is equal to 13.67. Next one, 19, 23, 26, so on and so forth. We're always gaining the last 3 pieces of data to create our forecast over here. And what that ends up giving us is our last projection. And that would be 18, 16, and 14. 18, 16, and 14 divided by 3 is equal to 16. So our next projection is going to be 16. Wait, I'll show you that. Yeah. 18, 16, and 14 divided by 3 is equal to 16. Exponential smoothing on the same note uses an alpha rather than this basic calculation of adding 3 periods together for a 3-period moving average and then dividing by the end, or a 50 moving average where you add 50 items together and divide by the end 50. With exponential smoothing, what it does is it takes an alpha, let's say 0.20 alpha, and it multiplies it by the last period's actual demand, and then you subtract that from the forecast in order to get your projection. The mathematical equation right here, our forecast plus our alpha times our actual data minus our forecast is equal to our new forecast. That'll become more explicit here in a second. Actually, and I'll just scoot right through. Yeah, here we have a nice illustration of that. For instance, here we've got our actual data tonnage of 180 and our forecast of 175. So our forecast 175 plus our alpha of 0.10, we've got a 0.10 alpha times our actual minus our forecast is equal to our new forecast, 1.75. We then take that, I'm sorry, 175.5, 175.5 plus, which 175.5 is our forecast, plus 0.10 times 168, which is our actual, minus our forecast, and that gives us our new forecast. The beauty is that this smooths out the overall data. We'll see this more when we start working with QM for Windows, QM for Excel, and some of our other tools, so we can make predictions. And here it creates the mean absolute deviation. Again, what it's going to do is take those differences between the actual data and the forecast. 180 minus 175 is equal to 5. We add all that error up, and then we divide by 8, the number of quarters, and that gives us our mean absolute deviation of 10.31. And we can also see here on Excel where we're taking the 0.1 We're calculating our mean absolute deviation right here. We've got our data, and what it doesn't provide us is a graph, unfortunately. However, it does provide us with our next forecast of 178.5958, yeah, 5, so on and so forth. Sorry for the rush through this, but I've got to get it done within, a reasonable period of time. But spreadsheets really do provide an incredible ability to look at small and medium-sized forecasts. There are more advanced programs, and we'll be dealing with Excel, well, not SPSS or Minitab, but certainly Excel to do large time series or causal models. We'll look at the best model and its parameters. We'll also look at forecasting packages, such as QM for Windows, QM for Excel, to make decisions there. And it's a great tool for inventory planning and control, as well as really just making a forecast on sales or other items. But that's a quick overview, and I appreciate your attention.